it mean? Should make the screen bigger. What does it mean if two shapes are similar? So if I say, oh, the shape is similar to this shape, what do I mean? Mathematically, what does that mean? Think back to your grade 8, grade 9 geometry. What does it mean if shapes are similar? Anyone remember? Conceal it, nice. Okay, definitely deals with angles. I agree. So angles is very, very important when it comes to similarity. I'll chat about that a bit more later. Okay, what does congruency mean? Let's start there. If I say these shapes are congruent, what does that mean? I know it's been a while since we've done this stuff. Oh. Okay, I'm not going to waste time on a definition waiting. So let's have a look. So can you see, let's definitely mention angles, and angles is very, very important, particularly when it comes to similarity, which I'll outline for you guys in a second now. But let's just start with congruency, because whilst not here, is important to know. Okay, guys, sorry, I left my other camera. That's cool. So we're just going to have to deal with no camera. I'll put it on every now and then when I'm able to. It's very much my fault. Okay, so when we are talking about congruency, I'm going to start there because it's a little tangent and we'll deal with the similarity now. So just remember, congruency means your shapes that you're working with are identical. So they're identical in size, in shape, in not necessarily orientation, but in shape and size, they are identical. Now, there are 4 ways or 4 cases for congruency. Side, side, side. Cool. Side, side, side. Side, angle, side. Right angle, hypotenuse, side. As well as side, angle, angle. So congruency. Yeah, okay, that was sad. Congruency is identical shapes. So if we then go and talk about similarity, which is obviously our focus here today, similarity deals with shapes that are, sorry, there we go. Shapes that are the same, but are different sizes. They're in proportion. So these are shapes, let's actually reword the same shape, but different sizes. And really importantly, when we say different sizes, we're talking about them being in proportion. Okay, so it's not just a random size difference. It might be a case where you've got a triangle. I'm just going to go equilateral triangle because that's the easiest one to work with. Let's say we've got an equilateral triangle where all the side lengths are 3. A similar triangle, which is also equilateral, has side lengths 9. What we see is that it's tripled in size. Those are similar shapes. Now, Kanifile mentioned the fact that angles are very important here, and this is very true. Shapes that are similar will still have the same angles or same corresponding angles in size. So what I mean by that is if we think about an equilateral triangles, it doesn't matter how big they are, all have interior angles that are 60 degrees, all of them. So any similar shape that you work with will have the angles or still equaling the same size. So if we now look specifically at similar triangles, so it's sort of exactly what I've shown you here with your equilateral triangle of a 3-unit side and a 9-unit side. Equilateral triangles, once again, means that they're the same shape and same size. Oh, guys, same shape, different size. But we need to remember, and you learned this in, and that's what I'm saying, it was a while ago, we learned this in grade 9. We need to remember that if we want to prove similarity in triangles, there are only 2 ways to do it. So unlike congruency, where there's 4 cases, similarity, there's only 2. The first way is angle, 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 which is exactly what Kanisile said earlier. If you can show that your corresponding angles are all equal, you have shown that your shape is similar. So for example, let's say we had this beautiful looking triangle. Table, okay, whatever. And we could show that this was 80, 30. So let's maybe do some better maths here. Okay, you get the idea with my picture, it's not great. 20, 50, and 10. If you can then show that this is 120, 50, and 10, because you've got all 3 angles corresponding with each other, you've proven similarity. Okay, so that's one way that we prove similarity. This is the most common way that similarity is proven. I'm not saying it's the only way, but it is the most common and most often asked method of similarity proof. The second way we can prove that triangles are similar are to show, can't do my essays today, are to show that your sides are in proportion. And we've learned how to do that already because we've done our prop theorem. So those are the 2 ways that you can prove that a triangle is similar to another or to multiple different triangles. Those are the ways that we can do it. And what we need to remember is that we are going to be asked to prove triangles are similar. So as we go along, we will practice these 2 proofs. And like I say, most of the time it's angle, 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 but we need to be able to do it. Congruency doesn't come up as much as similarity. Congruency is used more in some of your circle theorem proofs. So if you go and have a look at the proofs uploaded on Google Classroom for you guys, you'll see that particularly the theorem that is line from center bisects chord, or line from center perpendicular to chord, that uses congruency in its proof. So you do need to know both. Similarity, excuse me, similarity is more examined in sort of like the method questions where you actually need to go and find answers, whereas the proof questions is often where congruency comes in. I'm not saying it can't come in elsewhere, but that is sort of how it's split. All right, so that is the general idea of similarity. We now need to, like I say, actually apply this idea to triangle questions. So I'm just going to wait here for 2 seconds in case you want a screenshot, and then we'll have a look at our first example. Okay, cool. So let's have a look at our first example here. So remember, guys, just read your question very carefully. Make sure you got all of the information that you need for the question before you just dive straight into it, particularly with geometry. Okay, I mean, there's many questions. I mean, you should be reading all of your questions anyways, but particularly when it comes to geometry, read your information first, then deal with the questions. So it says in triangle PST, so triangle PST is our big triangle that we've been given here. We've got lots of little triangles, but we're concerned with the yellow triangle. TS is perpendicular to PS, that's shown here with my right angle given to me, and RQ is perpendicular to PT. So if we have a look at that situation, RQ, so that blue line, is perpendicular to PT. So that is that blue right angle over there. We've then been asked a bunch of things that we need to go and do. So the first question is prove that the triangles are similar. Just remember, and I probably should have put it earlier, but it doesn't matter. this symbol over here means similar. The 3 horizontal lines means congruent. That's not how you spell congruent. Okay, so just bear in mind, 3 vertical lines similar, 3 horizontal lines congruent. So we want to prove some triangles are similar, and then we want to show that certain ratios and products are the same. Those last two we'll get to in a second, and I'll explain what it's asking and how we deal with it. Let's first deal with the similarity, especially because, like I say, this is really important, but it's also something that you last dealt with in grade 9. So it's been a while. Okay, guys, so if we want to prove that these triangles are similar, firstly, and particularly in diagrams like this where there's a few triangles going on and it's a little tricky to work out what's what on your diagram, I like to highlight the triangles. So I've got PRQ. So remember, you just follow the order. So P to R to Q. That's one triangle I want to prove similar to PST. So PST is the big triangle that we were given right at the start of my information. Okay, so in trying to prove similarity here, I need to look out for either angle, 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 or size and proportion. Now it's generally pretty clear which one you're going to use. Because in this case, I have been given absolutely no information about the sides. I don't even have a ratio in my information for my question. I'm definitely not going to try and prove size and proportion. I'm going to use angle, angle, angle. So the way we set up our answer is we first state what triangles we're working in. So we say in triangle PRQ and triangle. Okay, this is clearly not enjoying itself here. PRQ and triangle PST. Now, guys, also remember the order in which you write your letters for your triangle is very important. They should correspond with each other. So once we've proven similarity, we need to make sure that all the angles on the sides match up and correspond in terms of what angles are the same, what sides are then in proportion. Okay, and again, we'll chat about this in a second, particularly when we get to question B and C. All right, so I've got a suggestion in the chat already. R1 is equal to S because they're both 90 degrees. Lovely. Okay, so remember, I have to show that 3 angles are equal in these 2 triangles. And like we've been told already, R1 is equal to S. Now, guys, I know that this is 90 degrees because of angles on a straight line. So that one with the blue dot, I know it's 90 degrees because of angles on a straight line. And I know that angle PST is also equal to 90 degrees or angle S. So that's the first statement I can make. R1 is equal to angle S. You can say equals 90 degrees if you want, or in your reason, you could say both equal 90 degrees. It could also be given because technically that information is given to you. You do you. I prefer to write they're both equal to 90 and then my reason is given, but it's really fine. Okay, Morgan's given another suggestion here of the fact that P is a common angle. So if we have a look here, this angle P, if you look at my highlighted triangles, that falls in both the pink and the green triangle. So angle P, and again, there's different ways you can phrase this. You could say angle P is equal to angle P, and then give a reason, shared or common angle. I prefer to just go P is a shared angle. Or you could say common. But honestly, it doesn't matter. As long as you get across the point that it's in both triangles, we're good. Okay, now, if we just, for ourselves, understand what we've already said. So we have now said that R1 is equal to S. We've said that angle P is common. And now what you need to remember, guys, is once you have got 2 of your 3 angles, the third angle is automatically equal to each other. Because let's say, for example, we already know that the blue angle is 90. Oops. Why does it hate me? We already know the blue angle is 90. And let's just say, for example, angle P was 60. The only other possibility for my third angle in both triangles would be 30 degrees. So once you've proven 2 of your 3 angles are equal, the third angle is automatically equal. Now the third angle on the green triangle is this Q2. The third angle, my pink triangle, is angle T. So we can now say angle Q2 is equal to angle T. And the reason for that is because, again, we know that sum of angles in a triangle have to add up to 180 degrees. If I already know 2 of the 3 angles, and in both triangles they're the same, this third one has to be the same. So we will just use sum of angles in triangle as our reason here. Now that we've got the 3 angles similar, we can now therefore make a statement that triangle PRQ. Now we need to make sure my letters match up. So angle P in the pink triangle was the green dot, and that corresponds with the green dot as well in my green triangle. So that would be triangle P. If we now move on to angle R was the blue dot in my green triangle, and that corresponds to the blue dot at point S in my pink triangle, so P, S, and that therefore means, and we've already shown here that Q is the same as T, it corresponds to T. So we can say that those 2 triangles are similar, and my reason angle, angle, angle. Okay, so guys, once you've got 2 angles, you've got the third. There's no need to try to do anything more complicated. Once you have 2 of your 3 corresponding angles equal, the third is automatically. Oh my gosh, it's quite happening outside. Anywho, once you have that, you now have a lot of information. And I just want to discuss what this information actually is. So on the diagram, I've labeled the angles that correspond with each other. That's cool. I'm going to take off the purple and the green for now. I can put it back if we need it back. Okay, sorry. Similar triangles also tell us now which sides are in proportion with each other. Okay, so what that means is length PR, so the first 2 letters in my first triangle, that would be side PR. That corresponds to the first 2 letters in my other triangle. So that would be PS, which is that whole side over there. And you just keep going like that. So the next side would be RQ, which corresponds to ST. So RQ corresponds to ST. Okay. And finally, this one's a little more complex to see, but we can do it. We start with the first letter. Oh, come on. First letter and last letter. First letter and last letter. PQ. So this is now in a small triangle here. Corresponds to the length PT, which is that whole length over there. So when we're proving similarity, not only does it tell us which angles are equal to each other, it also tells us which sides are corresponding, which sides are corresponding, and so therefore which sides are in proportion to each other. And this is going to help us with our next question, because the next question is asking us to talk about which sides are in proportion to each other, which sides have a ratio that we can now discuss their relationship. So when we approach this next question, we now need to be very mindful of these sides I've just labeled as corresponding with each other. So if we now go to question B is asking me to show that the ratio of RQ to PQ is equal to SFT to PT. Now, hopefully what you can see is that all of those sides I've actually labeled already in my similar triangles. So your first step here when you have a situation like this where you're trying to prove ratios are equal is you write down exactly what we've just identified. So what I mean by that is side PR is in proportion to side PS. So that was the pink that I highlighted. I know it's a lot of colors, but I do, for those of you who are visual learners, it is quite useful. So those are the pink sides that we highlighted. That is in proportion to, because remember, similar shapes are in proportion. That is in proportion to, we go to the next two letters, RQ over ST. So that was the yellowy, orangey color that I used. Which is also equal to, because again, everything's in proportion, and it's the same proportion, PQ over PT, and that was the light blue that I highlighted. So whenever you get a ratio question like this, this is what you do. You write down all of the ratios that apply because these triangles are similar and they all now correspond with each other. And you now can go and see which ones are useful for you in terms of what you're wanting to show or what you're wanting to prove. So if we go back to our question, get the color here, right? Our question is dealing with RQ, PQ, ST, and PT. So we now want to find ratios that deal with this. So RQ is in the second ratio, PQ is in the third ratio, ST is in the second ratio, PT is in the third ratio. So that means I'm going to be working with those two ratios. I don't even need to stress about the first one. It doesn't feature in what I'm trying to prove here. So that means I'm concerned with working with PQ over ST is equal to PQ over PT. That involves, excuse me, that involves all of the side lengths that I want. Okay, so now that we've done that, we now need to get this ratio sorted. What I want you guys to remember is that a ratio, I don't know why I said PQ, that's RQ. A ratio and a fraction are basically the same bit of information. One is just written as a ratio and the other is written as a fraction. So now we need to see what we want. So I'm just going to put down here that our goal for what we're trying to prove is RQ to PQ equals ST to PT. Now, if I look at what I have, RQ is already on the left-hand side, but I somehow need to get this PQ to join it. PT is already on the right-hand side, but I somehow need to get this ST to join it. And this is where we just need to be able to manipulate our fractions, our expressions. Now, there's lots of different ways that you can go about doing this, guys. Like, you kind of need to decide what makes most sense to you. English today. So what you can hopefully see is that take my scribbles off. What you can apparently I'm not taking the scribbles off. What you can hopefully see is that in my numerators, I'm dealing with in my numerators, I'm comparing the numerators. That makes no sense. So let's maybe say it another way. In my ratio, I'm comparing RQ and RQ, RQ and PQ. That is a comparison of the two numerators, which is what I was saying as well. We need to get those two numerators together. And then I'm comparing ST and PT. Those are my two denominators. So I'm comparing or making a comparison with those values. So that actually means I can set up a ratio because remember, ratios represent comparisons between values, as does a fraction. So because I've got numerator to numerator and denominator to denominator, and because I know that because these triangles are similar, everything is in the same proportion, I know that that comparison is the same. Okay, so I know that this is, whilst not necessarily a super long answer, the understanding behind it is not the easiest. I'm fully aware of that fact. Okay, so what we want to do, I'm just going to rehash quickly. Once we've proven similarity, we need to look at which sides correspond with each other, so which sides are in proportion with each other, and we can set up those fractions. It is always going to be first two over first two in each triangle, second two over second two, first and last over first and last. Once you've done that, identify which side lengths you're going to use. You're not going to use all three fractions. You're going to use two and then manipulate from them. And then you need to identify what are you actually comparing. So remember, our goal was to compare numerator, numerator with denominator, denominator. And based on the ratios we already had, we had that. There was no need to do anything more. And because we already had that, we could set up the ratio. The ratio is possible because those triangles are similar, because those triangles' size are in proportion with each other. So again, I understand that that looks like very easy working out, but the logic and the thinking and the method behind it is a little more complex. So if you're not understanding something, please remember to just say so. So basically set up your ratios and then identify what it is you want from them. Right, I'm just going to take a second in case anyone needs to digest, process all of that. Otherwise, I'll have a look at question C now. I know that I still have to do question C. So I'm just going to give like 30 seconds in case you want to ask questions. Otherwise, we'll move on to question C. Because like I said, I get that this is not the easiest thing to just, oh, cool, I understand. So let's make sure we are comfortable before we move on. Okay, so guys, again, if you are feeling a bit stuck, feeling a bit confused, just ask. Like, obviously, it's my job. I will help you. But please just ask. I won't know unless you say something. Okay, so if we go to question C. So question C is actually pretty much the same idea as what question B is. But the idea now is that we're looking for products. So we're going to do exactly the same thing. So as I've just said, it's pretty much the same thing as question B. So we've got our ratios. You obviously don't need to rewrite all of them because you've got them here, but I'm going to rewrite them. PR over PS equals RQ over ST is equal to PQ over PT. And we do exactly the same thing. We look at what we want. What is our goal? What are we like trying to find here? And we then go identify that. So we've got PR, PT, PQ, PS. So there's PR, there's PT, here's PQ, here's PS. So this time I'm working with my first and my third ratios. Again, I don't need to work with all three. There's no need to do so. Okay. PR over PS is equal to PQ over PT. Now remember, those little dots means multiplication. So at some point, you're probably going to have to multiply. So bear that in mind. And if we look at what our goal is, I want PR and PT together, which means this PT needs to come over and join the PR. And then I want PQ and PS together, so that PS needs to come over and join the PQ. If you look at what I've just drawn, that's a cross multiplication situation. That's what we do. So PR times PT is equal to PQ times PS. That is exactly what I wanted to prove, and I've done that. So sometimes in these questions, there is a bit of manipulation that needs to happen, i.e. cross multiplication, swapping fractions. Often there's manipulation, but you just need to, once again, start with my ratios, pick which ones apply to the lengths that you are working with in the question, and then you manipulate it accordingly. So question D was a ratio question. So this is where we need to, like I say, look at what you're comparing. In this case, the RQ and the PQ were both numerators. So it's numerator compared to numerator, which we already had set up, denominator compared to denominator. Here in question C, it's a product question. So we are going to have to multiply these fractions in order to get rid of the division and introduce a product. So a bit like trig, a lot of manipulation that we have to deal with when it comes to these ratio questions, but the manipulation isn't super testy, super tricky. All right, so let's take a screenshot and then let's have a look at another. I said you try, let's see how we feel. Okay, guys, in the chat, do you feel ready to try one by yourselves? So just give me a thumbs up if you are. or do you need me to do the next one with you? So thumbs up, yes, I'm ready to try. Thumbs down, no, please don't leave me. Got one thumbs up. I'm only going to get one thumbs up. I'm going to assume everyone feels the same. Okay, I got one thumbs up, so I'm going to assume we're all okay to give it a try. So let's try this one. It's basically the same set of questions, so you can refer back to the screenshots you've just taken. Have a look at those. Try the similarity, the ratio, and then the product proof, and then we'll have a look. I'll give you, probably need 5-6 minutes, maybe a bit more. So give you 5, we'll see where you're at, and then we'll go from there. Please remember, ask questions if you need. Put in the chat, send me a direct message, unmute yourself, whatever you need. Okay, I'm going to give you another minute or two and then we'll have a look. Okay, let's have a look. Alrighty. So the triangles that you are wanting to prove similar is triangle PAB. So this is this triangle. Oh, God, that attempt at highlighting PAB. So the yellow triangle, and then triangle ABC, which is the slightly smaller little triangle on the side here. ABC. So those are the ones you're wanting to prove similar. Now remember, this indication, this situation over here is showing that they're equal, but you're also told that in the information of your question. You also have parallel lines, so bear that in mind. Okay, so to prove similarity, again, because we've got no information about the side lengths, the ratio is nothing. We're not going to use size and proportion. That's not possible. We're going to have to use angle, angle, angle. So B1 is equal to C, you were given that. A1 is equal to B2 because of your Z, your alternate angles, which obviously means if two of the three are equal, the third has to be equal. P is equal to A2. Make sure your order is correct. So if you say triangle PAB, the angle that corresponded with P was A, with A was B, and with B was C. So ABC and angle, angle, angle is your reason. When it comes to question B, remember, start by writing out the ratios according to the similarity you've just proven. Figure out which ratio is going to work for you and what you're trying to compare. Now, if you have a look at the question, it was PA to AB. PA to AB was numerator, denominator, which means that on the other side, you need to have numerator, denominator, which we do PBAC, PBAC. And so you can quite literally just write it straight from there into a fraction. What we want to see in these questions is your ability to write out the proportions or the fractions in terms of your corresponding sides. And then the last one, AB times AC is equal to BP times BC. Again, look at the fractions that you have, look at the fractions that you're using from your ratios that you've already set up. We only needed those two, and through, again, cross multiplication, you got essentially what you wanted to prove. Okay, so really important is the similarity here. If you can do the similarity, then hopefully you can set up the corresponding sides and then get what you need. Take a screenshot and then let's have a look at our last example here. Okay. So guys, the next example is a little more like what we can expect come tests and exams, because this is not, obviously we're not solely looking at similarity, we're going to incorporate proportion, but this is where this idea starts to come in. So we have been given a triangle ABC, and we've been told below DE is parallel to BC. Determine the lengths of DE and AE. All right, so a couple things I want to point out real quick. We're obviously going to try, well, at this point, I'm going to try not to use any proportion theorem just because we're practicing similarity. But just remember, if you are told that you've got a line parallel to one side of your triangle, it cuts the other sides in proportion. So AD is in proportion to DB, which is in proportion to AE to EC. So just remember that prop theorem does apply here, but obviously we're practicing similarity, so we're going to do similarity. But in a test or exam, you can use that. There's nothing wrong with that. All right, but for sake of, let's practice similarity. The only way you can show these sides are in proportion are to then show that your triangles are similar. So that's essentially the first thing that we want to do. We want to prove that our triangles are similar. Now, the triangles we have here, and obviously we need to actually identify what those are triangle ADE, so this sort of top triangle, and then triangle ABC, so the actual massive big triangle here. If I can prove that those two triangles are similar, what I'm able to prove is that their sides in proportion. And so what I'm able to then do is work out the lengths of those sides using that proportional relationship. Okay, so we first state in what triangles? So in triangle ADE and triangle ABC. We can check the order later, because remember the order has to be correct. We'll check it later. But for right now, I'm just stating what triangles I'm working in. Now, we have got information about the sides here, but I don't have enough information about all three sides of both triangles to show that everything's in proportion. I would need all side information to be able to do that. So what that means is that I'm going to have to use angle, angle, angle. So I need to give 3 reasons. I'll move this up in a second. The first one that I can very clearly see is that angle A is common to both triangles. So angle A is a shared or a common angle. And then remember, you've been given parallel lines. So what that means is that angle ADE corresponds to angle B down at the bottom here. So ADE is equal to angle B. You can just say B because there's no other angles there because of corresponding angles. And remember, anytime you use a parallel line reason, you have to state the parallel line. So DE parallel to BC. And then for your third angle, you've got 2 options. Because you know it's just angles in a triangle, you could use that. Or again, you can use corresponding angles because you still have those parallel lines. They are still corresponding angles. It's completely up to you what you prefer. So you'll get both marks. It's absolutely fine. So angle AD is equal to angle C. Mine is always just sum of angles in triangle for the third one. Because I know that's true. I don't then have to stress about getting the reason wrong. I know it's the truth. Right, so we've proven that the corresponding angles are equal. So therefore, triangle ABC is similar to, and now we match up the angles. So A corresponds with A. Angle B corresponds with angle D, so AD, which therefore means E is my last letter. So ABC is similar to ADE, and this is because of angle, angle, angle. So now that I've proven similarity, we can go and have a look at the lengths of those sides that I wanted. Because now I know that all sides of my triangle are in proportion. So this is now where I can go and make that statement. So I know that AB over, remember, first 2 over first 2, AD is equal to BC over DE. is equal to AC over AE. And this is because our corresponding sides are in proportion. Okay, now again, because we know what we're looking for, we pick the ratios that work for us. Now remember, we've got AD. So if we just do like a little checkbox exercise, I know what AD's length is. So I know what AD is. I know what BD is. Don't have a length there, so that's fine. I know what BC is. There's BC. And I know what EC is. Again, I don't have EC, but that's fine. I am looking for side DE. Okay, so if we sort of take what we already know, these two fractions are probably going to be the ones I'm looking with, or working with rather, because that's got the information that I have. That last fraction has absolutely nothing for me. Now, AB is this entire side length, which means technically you do also have AB, 15 plus 3. So 15 plus 3 is 18. Okay. Over AD, which is 15, is equal to BC, which is 21, over DE. Now I'm looking for DE. Now remember, fractions you can swap when you're working with these proportions. So I don't really like DE in my denominator. So if I bring DE up, it would be DE over 21, but then remember to flip the other fraction, 15 over 18. And now this is easy. DE is equal to 15 over 18 times 21. And so that means it is 17.5 units. So once you've got proportion, whether you've used prop theorem, whether you're using similarity to get to the fact that these triangles are in proportion, that's up to you. So once you know that they're in proportion with each other, you can now go and solve whatever it is you need to go and solve. Okay, so there's 3 minutes left, and I'm a bit worried I'm not going to get all the way done. So what I'm going to ask is that you go and solve for AE for me. It's hard if you've got the time. If you don't have the time, I do get it. But let's try and get AE's length, and we'll check what its length is on Monday's lesson.